The ruins of the solar system's oldest empires float in the freezing vacuum of space. These jagged remnants are all that remain of a generation of worlds that vanished long before Earth was fully formed. The iron masses displayed in museums are the physical corpses of these failed planets. They are the wreckage of a first attempt at building a solar system. 4.5 billion years ago, thousands of massive celestial bodies called planetesimals dominated the region around the infant sun. Holding a meteorite means holding a piece of a world that was destroyed during the solar system's first violent era of planetary construction. Chronicles were the first solid building blocks. These millimeter-sized spherical droplets of molten rock formed in the solar nebula, acting as the seeds for everything that would follow. Over millions of years, these tiny droplets constantly collided. Through accretion, they stuck together, building from clouds of dust into pebbles, boulders, and eventually massive planetary spheres. Once these bodies reached a critical mass, their own gravity began to dominate. They aggressively swept up the remaining debris in their orbits, scaling rapidly into worlds hundreds of miles wide. Gravity acted as the primary architect of this era. It favored the most massive structures, rewarding growth with the power to consume or destroy smaller neighbors. These early worlds generated immense internal heat through the decay of radioactive elements. At their peak, the internal temperature rose until the entire rocky structure melted into a sphere of magma. This heat triggered differentiation. Inside the liquid world, the heaviest elements, primarily iron and nickel, sank to form a dense metallic core. Lighter silicate rocks floated to the surface, cooling into a rocky crust, while green olivine crystals became trapped within the boundary layer. Within these stable, layered environments, complex chemistry was taking place. The heat and mineral variety allowed for the synthesis of organic compounds and amino acids. These planetesimals established the geological and chemical blueprints that Earth would later follow to support life. The rise of early Jupiter ended this period of stability. The gas giant's immense gravitational influence destabilized the orbits of the planetesimals, pulling them into chaotic, intersecting paths. When these massive worlds crossed paths, they met in hypervelocity collisions. The impacts were so energetic that they instantly shattered the planets, reducing their structured layers back into billions of fragments. The Empire was replaced by the asteroid belt. The fragments of cores, mantles, and crusts were cast into the void, condemned to wander as asteroids for eons. This destruction perfectly preserved their history. While rocks on Earth are constantly recycled by tectonic plates and weather, these fragments were frozen in a vacuum, keeping their primordial chemistry intact for 4 billion years. Gravitational interactions eventually nudge some of these fragments out of their stable orbits. If the timing is right, the ancient debris falls directly into Earth's path. Entering the atmosphere at tens of thousands of miles per hour creates extreme friction. This pressure transforms the freezing rock into a blinding fireball, illuminating the sky as a bolide. As the rock decelerates, the outer surface melts away through ablation. The remaining material cools rapidly to form a thin, black fusion crust, sealing the ancient interior away from the air. A cosmic journey that lasted 4.5 billion years ends in a few seconds of violent deceleration and searing heat. When a massive iron core fragment strikes the surface intact, it releases a tremendous amount of kinetic energy. This crater in Arizona was excavated in an instant by a piece of a world that died billions of years ago. Stony fragments are more fragile. They often disintegrate before they can hit the ground, creating concussive shockwaves that can flatten entire forests without leaving a crater behind. These atmospheric shockwaves can be powerful enough to collapse brick walls and shatter infrastructure in modern cities. We no longer treat these fireballs as religious omens. Instead, we have developed systems for mapping their trajectories and recovery zones to find and study the material they bring. These events serve as a physical reminder that Earth is not isolated. We are constantly interacting with the ruins of a much older, more violent version of our solar system. To study these remnants, scientists search the world's ancient featureless deserts. Places like the Nullarbor Plain make it easy to identify the dark, scorched rocks against the pale ground. The largest recovered specimens are the dense iron cores of the first planetesimals. Their durability allowed them to survive both the fall through the atmosphere and the thousands of years of weathering on Earth's surface. Scientists have identified prebiotic ingredients inside these rocks, including uracil, cytosine, and ribose. These are the building blocks required to form RNA and DNA. These molecules were synthesized inside the planetesimals long before Earth existed. They survived the destruction of those worlds, spent eons in the void, and were eventually delivered to our planet's surface. This delivery of organic building blocks suggests a deep connection between these ancient worlds and our own origin. If our biology grew from the chemical alphabet provided by these fragments, then every living thing on Earth carries a piece of a shattered empire in its code.